and today we're moving on from ionic bonding. I'm going to have a look at covalent bonding. So let's get stuck in. Covalent bonding we get when we get a non-metal bonds to another non-metal. So let's take a couple of typical non-metals. Let's take oxygen and hydrogen. So oxygen has got 2 electrons in its inner layer, its inner shell, and in its outer shell it's got 1, 2, 3, 4, 5, 6. Now when the oxygen here reacts with something like water, hydrogen comes along and it's got its electrons, and it's got 1 electron in its only shell, and this is what we get. Let's zoom in and have a look at this. Whoops, wrong way. I haven't yet mastered this yet. Now, as far as the hydrogen's concerned, what it wants to do is get a full inner shell. So we're looking for, in these, a complete basic shell. So we're looking to try and complete the shells, and we know the first shell has 2, the next shell has 8, and the next one would have 8, and so on. So for hydrogen, which is 1, it gains an extra electron here. It's sharing this electron. So we've got here the sharing of electrons, and we're going to call this a covalent bond. So hydrogen is happy, it's got 2 electrons. This one is also happy because it's got 2 electrons. And the oxygen is also happy because it's got 1, 2, 3, 4, 5, 6, 7, 8 electrons. So the oxygen feels that it's got a full shell, and the hydrogen also feels that it has a full shell because it is this sharing of electrons, and these make really quite strong bonds. So we've got this idea. Now let's take a different substance. Let's take carbon. Carbon has got here an inner shell, and its outer shell it's got 4 electrons. 1, 2, 3, 4. When it combines with hydrogen, the hydrogen supplies 1 electron, so each hydrogen feels that it's got 2 electrons, so they're happy, and the carbon atom needs 8, 1, 2, 3, 4, 5, 6, 7, 8 electrons, so that's happy. So we've got molecules that are relatively stable. It's hard enough to draw these, but in fact what they look like is slightly different. And let's go and have a look at what these might look like. So what I've got is some means of making different models, and I've got a collection of different ones here. I've got fully assembled models of fairly large structures. We'll have a look at these in a minute. I've got smaller molecules. In different forms, and this is made from molymod, and we'll have a look at those in a minute. But to start with, I'm going to have a look at these, because this is perhaps an easier way of having a look at. This is some of my favourite snatoms to have a look at. So let's take our carbon atom, and if we look at this ball, and we'll try and zoom in on it for you, you'll see it's got 1, 2, 3, 4 bonds. I'll put my fingers where they are. 4 bonds, all equally spaced. And when the hydrogen reacts with this, so this is methane, we get a molecule that is not sort of square, diamond sort of shape, but in fact this molecule is, it's got a triangular face here, another one there, another one there, and then one on the bottom. So it's got 4 triangular faces, which gives us a triangular base pyramid, or as it would be known, a tetrahedral. So we've got this basic structure of our atoms, and it's easier to see with these models than it is to try and see them with others. Let's have a look at a different one. This time we'll have a look at nitrogen. Nitrogen is blue, carbon is black, and the hydrogen is white. So here we've got 3 electrons, sort of binding sites, and if we join these on, then we get a molecule of nitrogen trihydride, or ammonia. So we've got carbon tetrahydride, commonly known as methane, and we've got this ammonia. Now, why is it this shape? Well, to see why, let's go and draw this. And back down here, I'm just going to zoom out, and we can see this is our molecule. So this is nitrogen. So let's try and just draw our nitrogen. On the periodic table, then, it's got 2 electrons in its inner layer, and in its outer shell it's got 1, 2, 3, 4, 5 electrons. Here it combines with hydrogen, 1, 2, and 3, and it gives us this idea that this is going to be a particular shape. But we've got this set here, these electrons. These are lone pair electrons, and what these lone pair electrons do is they're back here, I suppose, and they're forming the other part of this tetrahedron shape, this tetrahedral shape. So we are getting this tetrahedral shape, but one of the bonds basically is missing, and it's by this lone pair. We can see what this looks like in water using, first of all, the snatoms. So let's take my water, let's put the bonds on there. Now if you could imagine we've got some other bonds, then I might have another one down here and another one on top, and then I've got the shape of my methane molecule. But this lone pair here, this lone pair there, gives us sort of a very bent shaped molecule, that of water. Now we can see this better in the molymod. Here is my molecule of water, and here is the same molecule of water, but this time I've put in the lone pair of electrons, and molymod can enable me to do this one, so I can see my lone pair. So it's the same shape, it's this tetrahedral shape, but these lone pairs are sort of forming two invisible bits of this small molecule of water. Let's look at a few more. If I take another molecule, let's build something like ethane. Here I've got two carbon atoms. Now these carbon atoms are going to be joined together, and the other bonds are hydrogens. And that gives us this molecule of ethane. The sort of shape that we've got of this is, it's really a sort of triangular prism. If I look down here, you can see these atoms all line up. They do spin, of course. But we've got this basic structure here of ethane. So methane is one carbon, ethane two carbons. If I want to have three carbons, then I'll move those out of the way. Three carbons, we'll put on the hydrogens. 1, 2, 3, 4, 5, 6, 7 and 8. Each carbon atom still has 4 bonds. Here we've got 3 with hydrogen and 1 with a carbon-carbon bond. The middle one has only 2 hydrogens because it's got 2 carbon-carbon bonds, and the other end is the same as the first end with 3 hydrogen bonds and 1 carbon bond. And this molecule, you can see, is sort of arranged so that it doesn't matter which way you look at it, it's the same. It's basically symmetrical. So we've got here a family of covalent carbon compounds. These are hydrocarbons. This is methane, this is ethane, and this next one is propane. And if I were to join my propane with another one, this makes a 4 carbon chain. This will be butane. We can take one of those off and put another one here. This makes a 5 carbon chain. This is pentane. 1, 2, 3, 4, 5 carbons. And after you've gone through the first ones of methane, ethane, propane and butane, they get easier to name because there's pent for 5, and then we have hex for 6, and I've got het for 7, and I'll do one more. I've got oct for 8, an 8 carbon chain. And these things do move around. People think that they are basically in one particular orientation, like a long sausage shape. But in fact, all these molecules move around all the time, and they change their shape. So we've got a family of carbon compounds. Let's just take these to bits and we'll have a look at some other ones. The good thing about atoms is that they come apart really quickly and easily. Boy, they're some of my favourite molecules to look at. Right, let's have a look at a different molecule. We've looked at water. This time let's look at carbon dioxide. Now carbon dioxide is CO2. The carbon's got 4 bonds and the oxygen has 2. So I'm going to use some extra little shapes here to try and show that instead of having 1 bond between an atom, that we can actually have 2 bonds between an atom. And there is a molecule of carbon dioxide. Very different in shape to the molecule of water. The molecule of water here is bent and it gives rise to lots of water's properties. And carbon dioxide is a very different shape. It's a linear molecule, and this gives rise to some of its peculiar properties. Let's see how we would draw one of these. So let's take a look at the molecule, and we've got it here, and you can see quite close up these bonds. So let's draw our carbon. So our carbon has 2 electrons in its inner layer, and in its outer layer it's got 4. I'm arranging them slightly differently than last time. Let's now draw in an atom of oxygen. Oxygen has got, I'll draw these as circles here just so you can see them different. It's got its 2 lone pair, and its other 2 electrons are shared with the carbon. Let's do that one again. Two lone pairs, and the other one shared with the carbon atom. And the oxygen needs 8. 1, 2, 3, 4, 5, 6, 7, 8. The same on the other side. And the carbon needs 8 to have a full shell. 1, 2, 3, 4, 5, 6, 7, 8. So all the atoms are happy that they've got their full shell. And we would draw this molecule out slightly differently sometimes. And I would draw it from my carbon with a double bond going to the oxygen. So I draw it like this rather than perhaps just writing it down as CO2. So this is more of a layout, structural formula. And that signifies these double bonds? Well, we've looked at a single bond, and if I draw out my nitrogen, then I can draw it out like that, or I can draw it out as NH3. Back to our methane, I could have written that with a sort of a stick diagram to show one bond, or I could have written it out as CH4. Water, we've got that one as HOH, or more commonly H2O. That's double bonds. Can we do anything and have things like triple bonds? Yeah, sure we can. Let's go and have a look at those. I've got two nitrogens. The nitrogen has 3 bonds, and using these little sticks again, I can place them this time the other way round. I've got one for doing a double bond, and then I've got a different side for a triple bond. So let's put all the triple bonds on there, and I'm going to get them all facing the same way. Here's my molecule with its faces the same way, and there is a triple bond forming nitrogen gas, which is N2, and it's got this triple bond sharing of electrons. Would you like to have a look at this one as it's drawn? You don't have the option, the answer is yes. Let's see what we can do with this molecule. I've got my nitrogen. It's got 2 in its first layer. It's got 1, 2, 3, 4, 5 in its outer layer. Let's join that to another nitrogen. This time I'll do this one with circles. These are just electrons, they are exactly the same. And we've got 1, 2, 3. So I'm sharing that, that and that. 3 pairs of electrons shared and another lone pair either side. And that is our structure of nitrogen. What about oxygen gas? Let's have a look at this one. Oxygen gas would be similar to the nitrogen, but instead of it having 3 bonds, oxygen has only got 2 bonding points. So I'm going to use the double bonding point here, and there is a molecule of oxygen with its double bond. We've seen that carbon can do a double bond. Let's look at this in more detail. I can double bond 2 carbons together. I'm just going to have a quick tidy up. My carbon is going to be double bonded to another carbon. That means it's only got 2 more bonding sites left. And we get a molecule here. This is ethene. Let's compare it with ethane. It's only got 1 single bond between the carbons. And there we've got the difference between ethene and ethane. Ethane is not really a useful chemical. We can burn it. Let's think of what else we can do with it. Yeah, did I mention we can burn it? Yeah, and that's about it really. There's not much useful things we can actually do with the ethane. But ethene, on the other hand, is a very useful molecule. It's got a double bond, which is much more reactive than the single bond. So this will break and it will react with all manner of different chemicals. I could break this bond and I could just simply add hydrogen to make my ethane. But that would be really a bit of a waste. So if I've got my double bond, I could react it with another chemical, like bromine. So as we break the double bond, we make a molecule here, which is bromoethane. And interestingly, if you add bromine, which is sort of a brownish colour, to ethene, the reaction happens quite spontaneously and it changes from this brown colour to a clear colour, because this is clear. And in fact that is a very good test for the alkenes. We can try them with bromine, water, and we can see that they will change. We can put all manner of chemicals in here. And if I take several of these molecules, so let's take another one. We've got here 2 ethene molecules. Let's go mad, let's have a third. Now I've got a collection of ethene molecules, and if we can heat them up and we can put them under pressure, then these bonds will break. And as they break, the 2 molecules join together, and another one will join to that, and so on and so on and so on, forming not just a little chain here of 6 carbons, but maybe chains that are 1,000,000 molecules long. And we'll say, well, we've got from 1 methane to ethane, propane, butane, pentane, hexane, but we've got lots. Let's call it poly. Poly meaning lots, and so this will be polyethane, or more commonly called polythene. And we can make from these alkenes plastics, which makes this a very useful commodity. Right, we'll just put these away, ready to do the next one. We can look at various other molecules. Let's just make one up here. If I can react water with my ethene, which is easier than ethane, we can shove a water molecule on there. And we make what a lot of my students think is a rather nice little dog. But this molecule is eth, and it's got the alcohol group, the ol, so ethanol. So this is alcohol, most students' favourite drink, although I don't know why, because this is in fact a poison. If we look at it in its shorter form, with only one carbon, here we've got another small molecule, and this is methanol, and this is not particularly good to drink because it kills you. Not immediately, but it will kill you fairly quickly. So this is methanol. With one more carbon on there, we've got ethanol, which is still a little bit toxic, but people do drink it. And then if you want to, we can add on another carbon, and this is going to make propanolol. And that really isn't very nice to drink at all. That tastes horrible. It smells particularly horrible. Some countries they call it rubbing alcohol. And one of the interesting things here about this molecule is that I could swap them round like that. And this is a different alcohol. At this end, or the other, this is called propanol. Propan, because it's pro, like propane, propene. This is propan, and it's called 1-ol because it's stuffed at the end. We start labelling our carbons from this end, 1, where the group is. So it's propan 1-ol. If I have it in this position, it's propan 2-ol because it's labelled from this end. If you don't like labelling it from this end, you can do it from that end instead, and that's 1, 2. As you see, exactly the same chemical. And this is sometimes called isopropyl alcohol. And again, it doesn't taste very nice, and it doesn't do you an awful lot of good if you drink it. So we've got then another group of chemicals, methanol with 1 carbon, ethanol with 2 carbons. Then we've got propanol, 2 forms, propan 1-ol, propan 2-ol, with 3 carbons. And if I take another one, then we've got, if I shove this at the beginning, this is butanol. So butan, because it's got 4 carbons, and ol, because it's got the OH. And this can be butan 1-ol, stick it on this end, now to the middle, this is butan 2-ol. Now this is where it gets clever, that if we put it on the 3rd carbon, a lot of students think this is going to be butan 3-ol, but if I turn it round, you'll see that it's back to butan 2-ol, and it doesn't matter which way you put this round, it's still butan 2-ol, whether this is on this carbon or whether I put it on that carbon. Butan 2-ol. Okay, so we've got these fairly small molecules. Now let's look at some of these properties of these small molecules. So I've just made some water. Put them out of the way. Here are two water molecules. Now, all the bonds are full on these. There are no spare bonds. And so these molecules don't join well together. And so these small, simple molecules tend to have fairly low melting points and boiling points. Let's look at methane. It's the same. If I put my hydrogens on here, all the bonds are used up. And if I bring another one in here, like the water, they've got no bonds to share. They will not stick together. So these are small covalent molecules, and because they've got no bonds left over, they don't stick well together, and this gives rise to their property of having a very low melting point and a very low boiling point. So this substance here is a gas at room temperature. Water is actually slightly different. Now, let's go and have a look at this water and see what I mean. We'll use this time the Molly mod because it's easier to see on the piece of paper. Now, these molecules of water here, let's just draw one out. So we'll do the oxygen with its 2 electrons in the first layer. It's got its lone pair electrons in the next layer, and this is shared with the hydrogen. And there is my covalent structure of water. There's something else special about water, and what it is, it's got quite a lot of nuclear material here. So when I draw this out, these electrons are drawn very, very slightly closer to the oxygen and further away from the hydrogen. So this makes the hydrogen just a little bit positive, and the symbol delta in Greek is used to mean a little. So this is delta positive as well. And the oxygen's very, very slightly more negative. And what happens if we get negatives and positives? Well, they attract one another. So I've got this lone pair here, and this lone pair is more negative, and it's going to attract the positive hydrogen towards it. So we're getting a sort of a structure here. We better have a look at that. In a little bit more detail, we can see here the structure of water. In fact, this is the structure of ice, because the molecules here have got these extra little bonds between them. So here is my water molecule with its little electrons here as a lone pair, and our hydrogens set apart. And we've got this very, very weak bond. It's called a hydrogen bond. And although it's particularly weak, with enough of them, this becomes actually something that's quite strong. And it gives rise to a really good experiment that you can try with water. That you can actually manage to make something float on water, like a piece of iron. And we can make things do that because of these hydrogen bonds. They're so strong they can actually support various things. And we call that water's surface tension. And I was going to try a little experiment out, but I'm not, because we haven't got all day for me to try and get the needle to float on the water. Let's look at carbon. Carbon here, it's got some bonds. Let's just join them together. And it's forming this sort of tetrahedral shape. And I can put in perhaps another little tetrahedral shape. There we are, there's another one. And when I do form carbon together, it can form little sort of basically shapes like this. This is a tetrahedral shape, and I can't really see it with all of these molecules, so let's try and make this a little bit bigger. Here's one I prepared earlier. And what we've got little rings of 6 carbons. You can see 1, 2, 3 in all directions, forming a really strong tetrahedral shape. Each carbon is joined to another carbon, and each carbon's joined using all its 4 bonds. So if I put some more carbon in here, it just joins onto these, making more rings, building up a rather large crystal of carbon. And this crystal of carbon has a name, and it's called diamond. Very, very hard, very, very strong. Let's compare that with another molecule of carbon, and this one, we've still got those 6 rings all joined together, very, very strong, but that leaves one bond of carbon undone. And these form very weak bonds with the layer below. So we've got lots of layers of carbon on top of one another. And this is called graphite. So very easily with graphite we can shear off this layer. Let's see that. If I draw this out for you, let's see what happens. So there's my molecule of graphite, and here is my layer of graphite from my pencil. And if I rub my finger across there and then rub it across, you can very faintly see a little line. And this little line is probably getting towards 1 molecule thick layer of graphite. And we'll give this a name. And we're going to call this graphene. And in fact, because it's made up of these strong layers, and this layer here is incredibly tough, incredibly strong, what I can do is I can take this layer and either wrap it up into a tube, or I could take it and I could wrap it up into a ball. And here it's been wrapped up into a ball of about 60 carbon atoms. And this is a molecule called a Buckminster Fullerene, named after the person who discovered or made them first, a gentleman called Buckminster Fuller. So these Buckminster Fullerenes, or Fullerenes for short, are potentially really useful. They've got some of the properties of graphite. Graphite has got extra electrons, so graphite can conduct electricity, particularly well in one way rather than the other. And so this Buckminster Fullerene or buckyball, sometimes called, can also conduct electricity. I can take a sheet of this and I can wrap it up to form a tube, and this then makes something called carbon nanotubes. It's not going to catch on, that name, really, is it? A carbon nanotube. Let's give it a better name. And what we can do is we could decide that a better name for this might be a carbon fibre. So we've got diamond for one form of this. I need to zoom out. We've got diamond, we've got graphite. Diamond doesn't conduct electricity, graphite does. Graphite, we can take a layer off called graphene, and this graphene we can either make into a tube, and we're going to call this carbon fibre, or we can roll it up into a sphere and call it a Buckminster Fullerene. So we've got quite a few different forms of carbon, and these are given names, diamond, graphite, graphene, so on, but they're called collectively allotropes. They are the allotropes, or different forms of carbon. And other substances also have these. Sulfur is a very good example. We can play with various different forms of sulfur. These molecules all join together. So we've got two types of covalent bonds as we see them. We see either these small molecules that can't well fit together, and they have low boiling points, low melting points. Substances such as methane, water. Water's a little bit of an abnormal substance, but not that different. Or we can have these giant covalent structures, and these all typically have very high boiling points and melting points in the region of several thousand degrees, 3,000 odd degrees for diamond. Or graphite, which has got exactly the same melting point as this one, the diamond. And in fact, these two have a peculiar property that they don't have a liquid phase. It goes straight from a solid to a gas. Same is also true of the Buckminster Fullerene. So I hope that's given you an idea about covalent structures. We've looked at what a covalent bond looks like, the single bond, the double bond, the triple bond. We can see that some of them have families, names, which we'll learn more about those later. We've got the simple covalent bonds, which have low boiling points, low melting points, such as methane, oxygen, nitrogen. They form most of the gases that we breathe in, which are all small, simple covalent structures. Or we have the larger, giant covalent structures, diamond, graphite, and other peculiar ones such as silicon dioxide, sand, and that has a similar structure to the diamond, which is why it's also very hard. Covalent compounds. I'll talk more next time when I see you. If you like what you've seen, subscribe, and I will see you in the next one. Take care. Bye bye.